Good evening. Can you hear me?
Good evening, sir.
Yeah, so I think we had discussed structural isomerism in coordination, right?
Yes, sir.
Okay. Okay. So the last part of this chapter is stereoisomerism. Stereoisomerism in coordination compound. We all know the definition. The stereoisomerism is because of the relative position of atoms or groups in their space, right? So we know two types of isomerism this has. One is geometrical. Geometrical isomerism, and the other one is optical. Geometrical and optical. Okay. Now, to understand the geometrical and optical isomerism, you should understand first of all the geometry also. What is the geometry of the molecule and how to represent the geometry, right? So, the geometrical isomerism will take few assumption here, and the assumption is the central metal atom is represented by M. This is one thing. Monodentate ligands are represented by small letters A, B, C, D, and so on. By small letters A, B, C, D, E, F. Then we have symmetrical bidentate ligand. Is represented by symmetrical means both atoms are same. right? Symmetrical is not because of the structure, but it is because of the donor atoms. If both donor atoms are same, then it is symmetrical bidentate ligand. That's why we assume it as AABB capital letter, right? And unsymmetrical bidentate ligand is represented by AB, CD, EF, etc. This is the notation we are going to use. Acha, we'll see that Venkat in the last.
Sure, sir.
Yeah. Okay, so these are the notations we are going to use. Correct. Now, we are going to see the geometrical isomers of compounds with different coordination number. The most important one we have, coordination number 6. Coordination number 6. So the first type of complex we can have with coordination number 6, and I am considering complex with all monodentate ligand, right? The first type is complex with all monodentate ligand. The first example is we have MA6 type. What is MA6 type? What do you mean by this?
Sir, all the surroundings are the same.
6 monodentate ligands.
And same ligand is being surrounded that.
Yeah.
Yes. So there are 6 monodentate ligands, and all ligands are similar. Right? We have 6 monodentate ligands. So obviously the coordination number 6 we have, its geometry is what? Its geometry is octahedral, right? So how these 6 ligands are arranged around the metal M, that we need to understand here. And by changing the position of the ligand, do we get different structures or not? If we get different structures, then the isomer possible. Otherwise, it does not show isomerism. For example, you see this. How do we represent this MA6 type molecule? It has octahedral geometry, and we have to place metal here at the center, and 6 ligands are present at the corners of an octahedron, which is nothing but this. Right? Now you see, since all ligands are same, anywhere if you change the position of A, right? This A you place here, this A you place here, this does not make any difference. right? Hence, in this case, we have no geometrical isomerism possible, no GI for this. Did you understand this?
Yes, sir.
Any doubt?
No, sir.
Another type of molecule you see, Ma5B type. 5 monodentate ligands of identical monodentate ligands, 5, and one is different from the other. Okay, so how do we place this? Again, the geometry is octahedral. Metal is present here at the center, and wherever you want, you can place this B and the 5A atom. For example, I am placing 5A atoms here at the corner of this square, 1A on the top, and B here on the bottom. Wherever you want, you can place it. That's not a problem. Okay, one molecule is this. Can we draw one more molecule here? M here, A, I'll place B here, A here. Tell me, is this possible?
Yes, sir.
That's the same only.
What?
So the both are the same only. So all bond lengths and all everything is same.
And why it is same?
So all the bond lengths, bond angles are all the same.
Yes, all the 6 positions are equivalent position here. Right, that's why A or B, whatever structure you write first or second, both are the same structure we have, right? Because the relative position is same. You see, this B will have at a certain distance, we have A, all these A present. Here also we have same kind of thing, right? Hence, both molecules are identical, same molecules, and we do not have geometrical isomerism possible in this kind of complex. Okay, could you tell me what is the angle this one?
Right.
Is it 90 degree?
Yes.
Yes. Yeah. Right. So this angle is 90 degree. You see, the square is in the plane. Imagine the the screen of the computer or laptop, whatever. Right. The screen is the square. So this A is coming towards you. This A, one of the A, and the other one is going behind the screen away from you. Like that, you can imagine tetrahedral, octahedral geometry. Is it right? Are you able to imagine this?
Yes, sir.
Right? So this A is coming towards you, and this one is going behind the screen away from you. So this is octahedral geometry. So obviously this A, this line, and the plane of the square are perpendicular. Angle is 90 degree. What is this angle here? This angle is also 90 degree.
Yes,
What
sir.
is this angle?
One.
180 degrees.
180.
Yes, it's 180 degree. Right. Actual structure you must understand. How this octahedral looks like. Okay, similarly, if we take third type of complex, which is Ma4B2 type, could you tell me how many GIs possible, if possible, then?
Three.
3.
Yes, sir.
Okay. Okay, all of you are getting 3?
Just a minute, sir, please.
No, Shamik is getting 2. Others tell me. Okay, Shamik is getting 2. Okay. Tripan is getting 2. Venkat, what about you? Okay, Pratham is getting 3.
Doing, sir, 1 minute.
Amana, Niyati, Advaita is there? Yes.
Yes, sir.
Sir, I got 3.
Okay, Amala is getting 2, Dhyan is getting 2. Fine, guys, you see, whenever you get this kind of question, suppose, if any example you have, then best way is what? You write down in this form actually, A4, B2 type, so that you can easily, draw the structure. Because you cannot memorize this, there are so many possibilities, right? We are going to discuss all the possibilities here, but in the exam, you should know how to draw the structures, right? Okay, Kirtana is getting 2. Fine. So first of all, what you do, what you have to do here, you have to draw the various possible structures first. Most of you are getting 3, so I'm drawing 3 square here. When you draw this 3 square, and obviously metal we have at the center of the square, in all the structures, metal will have at the center. Now randomly you place all the ligands around this metal at the corner of the octahedron. Whatever you want, wherever you want, you can place. For example, suppose I am placing all the A at the corner of the square. This is one possibility. And the 2B like this. This is one possible structure you can draw. Now what you do? This A and B are exchange. A, B, A. This is B and this is A. This is another possibility. Okay. What is the another possibility we have? Can we change the position of B here in this square? Or I'll change the position of this B. Suppose I place this B here, A here, B here, A here, alternate.
So isn't it the same as the first one?
Same as the,
First one.
okay. What is the another, is there any other possibility?
So in the second one, if we interchange the top B with the right A.
This one,
Yes, sir.
okay. A, B, A and B. This is what you're saying, Anjali?
Yes, sir. This one.
Tell me. Any other possibility? Could we draw anything else here?
Sir, isn't second and fourth equivalent?
Okay. I'll tell you that, wait. Any other possibility you see that we can draw? Okay, no. So, first of all, in the exam, obviously, if you do some practice, you don't have to draw all the structures. You could identify this easily, that how many structures we can draw. But suppose if you do not know, you just draw like this all the possible structure, whatever you feel like the possible structure we have for the complex. You draw it like this. Now you have to then analyze that whether the drawn structure that you have drawn, right, whether the structure you have drawn are identical or different structures. Because a number of different structures are the geometrical isomers here. So you need to first identify also after drawing the structure that they are same or different. Now, how to identify the given molecules are same or different? Okay. So for this, what we do, we just take the reference structure. Like suppose the first one, this structure I take as a reference one. Right, 1, 2, 3, and first structure, we take it as a reference one. And the first structure, at the corner of the square, we have all A ligand present. So in other structure also, we'll try to draw a square and the corner of the square contains all A ligand. Like suppose this one. In this one, could you think of this particular structure? This is square you see. This is square. So when you rotate the molecule like this, it becomes the same as the first molecule. So what we can say, first and third are equivalent structure. Is it clear? Similarly, first and second are different structure. We cannot compare first and second. Wait, Dhyan, just a second. Second one you see, we have 3 A atoms at the corner and 1 B. So if you want to compare first and fourth, these two are different structures. If you want to compare second and fourth, so 3 A at the corner and 1 B. So we can easily draw this square hypothetically. We can think of this square which contains 3A at the corner and 1B here at the corner. It means this second and fourth are also the similar structure. This is one way, one of the ways to identify whether the given structure is identical or different structures. Did you understand this?
Yes, sir.
Yes, sir.
Got it? Okay. This is the one of the ways, right? One also thing you can think of. One also way you can think of. We can draw trans isomer in this. We can define cis and trans isomer here. And cis and trans isomer we define by the relative position of the atom. Like you see, if the 2B atom present at 180 degree, the 2B atom present at 180 degree, this is trans isomer. If B present at 180 degree, okay. Here you see the 2B atom, the angle between this B and this B, this bond, it is 90 degree, right? So when the bond angle is 90 degree here, then it is cis isomer. So this one is cis, this one is trans. And if you look at the bond angle here between B and B, it is 180. Here also it is 180 if you look at this. And that's why first and third are the same thing. Second and fourth, you see the bond angle is 90, hence these two are also same. Is it clear?
Yes, sir.
You need to change the relative position. If it is not changing, then the molecule is same, identical only. Here if you compare, another thing also here, if you compare, the 2B is at 90 degree from all the A ligand, right? Here also we have the same thing. This B, if you see, it is at 90 degree from all the A ligand. You see, this angle is 90, this angle is 90, this angle is 90, this angle is also 90. All the angles are 90 here. Hence, the molecules are identical. Many different ways you can think of this structure, right? So you don't have to memorize this. Once you once you finish this, you will easily identify that what are the possible structures we can draw. Okay. Now another one you see, fourth type of molecule, Ma3B2C type molecule. Tell me, if GI possible, then how many GI should be there? Okay, done. How many isomers you're getting? 3. Venkat, wait. Okay, so the structures are 1, 2, 3A and 1C. So 1C, this is one structure. Another one is this. Another one is this. Next we can draw A, B and C. Which are B we have. This is B. You can also think of this structure B, C, M, A. Okay, like this you can draw many structures, but again you have to compare whether the drawn structure is same or different, right? So here you see we have 3A at the corner. With respect to B, we can say B is at 180. Here B is at 90. So these two structures are different, definitely. Okay, this one I have written 4A here. I'll just change this. Suppose B I'll place over here. B I'll place over here. So this two, the B are at 90 degree to B atom. Here also B at 90 degree. Right? Here B at 180 degree. Here B at 180 degree. And here the 2B atom, where is they have written 4A. What I have done. This is C, this is D, for example. Okay, so here the 2B atom are at 90 degree again. So let us try and draw a square which contains 3A and 1C. Okay, 3A and 1C we cannot draw over here, but here we can draw 3A and 1C. Can we do that? No, here also we cannot do that. 3A and 1C we can draw it here. You see this. Right. So first, second, third, fourth and fifth. So we can say first and fourth are identical structure. 3A and 1C, we cannot draw it here. Right. First and fourth are same. If you look at this one, 2A, 1B and 1C. Okay. So we can have 2A, 1B and 1C. If you look at this one and this one here, this structure for second one and fifth one, are they similar structure or different structures?
They are different.
So which one?
Second one and fifth one.
They're different, sir.
Different. So first, second and fifth are different. What about second and third? Second and third are also different, but third and fifth are the same structure. Third and fifth are the same structure. Because you see, we can have 2A, B and C a square like this. So third and fifth are the same structure. So the three isomers we have first one as an isomer, we have second one and third one. These three isomers we get in this molecule. Okay.
Sir,
Tell me.
Sir, I didn't understand how second and fifth are different.
Second and fifth.
Yeah, sir.
You see, in the second one, we have 2A, B and C. Here also we have 2A, B and C. But the position of A you see here, it is at 90 degree. And here the 2A at 180.
Oh, right. Yes, sir.
B and C are at 90 degree here. B and C are at 180 degree.
Okay. Yes, sir.
Right.
Yes, sir.
So with respect to A, we can say this molecule is cis isomer. This one is with respect to A. Identical atoms we have to see. With respect to B and C, we cannot say. With respect to A, it is cis isomer, and this one is trans isomer. B or C we can also take here. cis this one and trans this one. Okay, so 1, 2nd, and 3rd are the different structures. 4th and 5th you want, you can draw, but these are the similar structures that we have already drawn. Now the problem is that this kind of question, if you try to solve by this method, it takes a lot of time in the exam. Okay, so what is the best way you need to do here? And this is the method you are going to use in the exam. You don't have to draw these structures. It takes a lot of time. Just to consider A3B2C we have here, molecule. So the molecule we have is M A3B2C. What you need to do, you need to, write down the ligands in a pair, right? 2 ligands in a pair, 3 groups you have to form. 3 different possibilities, 3 groups you have to form. Like you see this A3B2AC, how you can, form 3 groups in a pair. We can write both A together, then one A we can write with another B, and the another B we can write with C. This is one group we get. Another one, what we can write, we exchange A and B here, A and BC. So we can write AB. This AB you let it be middle wala as it is. AB and AC we can write another one. Right, BB we did not write together. So we write down AA together. Then here we write down BB together, and then AC together. So these are the 3 different, possibility you can write. Any other possibility you can try, you won't get. Right?
Yes, sir.
So this actually, if you want to draw the structure after this, you see how do we draw the structure? See here, this pair actually represents the ligand which is present at the opposite corner of a diagonal. This pair, and this pair. You see AA. AA is present, AA, AB, AC. Just a second, AA, AB, AC. AA, AB, BC. Okay. You see this molecule here. The 2 ligands present at the opposite corners are A, bracket close. Another 2, we have BC, bracket close. Another 2, we have AB, bracket close. Whether you write this BC here or AB here, that won't make any difference, right? But this molecule, this arrangement, we can draw like this. Did you get my point? Similarly, here you see for this one it would be 2AA, like 2A at the opposite corner, AC at the opposite corner, and here we have what? Here we have BB. This one you see here we have AA, BB, AC. This is the 3rd one we have. This one it would be AB, then AC, then AB again, 2nd one. So like this, you can frame different pairs of 2 ligands at a time, and 3 groups you need to form here, since it is octahedral. Did you understand this? It gives you the number of isomer that you get over here. See, if you go back and do it for the other molecules, that also fine, you can do it. You see for this one, A4 and B2. Consider this. A4 and B2. So what we can write? We can write AA. Again, we can write AA. We can write BB. This is one isomer. AA, AB, AB. This is another isomer. So these are the 2 isomers possible here. You can see here, we won't get any 3rd possibility like this. Clear? Understood?
Oh, yes, sir.
Right? So if they ask you the number of isomers, you have to draw like this. You don't have to draw these structures in the exam. It takes a lot of time, but yes, you should have the understanding that when you have written the ligands like this in a pair, then how the molecule looks like, how can we draw the structure with this particular input, right? All these pairs are present at the opposite corner of a diagonal.
So where exactly are these pairs drawn again?
Diagonal opposite.
Okay.
Let's suppose you don't have anything, right? You just have these pairs. So how do we draw it?
AA and all.
A square बना लो, and then we have a metal here in the center. AA है यहाँ पे, so we'll place AA here like this, कहीं भी opposite. AA again, so A and A, and we have BB, so B. This is
yes,
one of the structure. Right. And this one, if you write like this, AA, BB, AA, this one and this one are the same thing, right?
Yes, sir.
All of you understood?
Yes, sir.
So this saves you time in the exam. So must take care of this, how to draw the structure. Now, on the basis of this only, I am not going to draw that octahedral structure now. Just I am writing down the complex. You tell me how many isomers possible for this, if possible then. Okay, like you see the another one, I think it is a fourth one. Fourth or fifth one? Fourth one, I guess, right? No, fifth one.
Yes, sir.
Yeah, fifth one. Tell me how many isomers we have here. Ma3, B, C, D type. You see all these are monodentate ligands. How many isomers we have here in Ma2, B2 and C2 type? Done? Okay. So first one we are getting 4 and the second one we are getting. Okay, so arrangement, the possible arrangement here are, we can write down AA, then we can write down AB and CD. Then we'll have AA, then AC, BD. Again, we'll write down AD together. So AA, AD, BC, and one more we have AB, AC. There are 4 isomers possible for the first one. Okay. Second one, we can have AA, BB, CC, AB, AB, CC. And when we have AA, BC, BC, AC, BB, AC, then AB, AC, BC. 5 GI possible for this. Is it correct? Okay. Now, one very important point here, it is what? That out of this 5 geometrical isomers, this one, the last one that I have written here, this one is optically active also. Optically active. You must take care of. There is no plane of symmetry in this. Similarly, you can draw for another molecules, like we have MA2B2CD type, and in this we have 6 GI possible. MA2BCDE type, in this we have 9 GI possible. And last one we have MABCDEF type. In this we have 15 GI possible. Okay, and here we get this one. This has been asked in NEET exam, the last one. Fourth one, which one? This one, the 5th one.
No, sir, the MA3BCD.
AB, AC, AD. You're talking about the 4th one.
Case 5, the 4th sub example.
AC, AD you're talking about.
ABSAD, yes, sir.
You see this? AB, this also we can say.
Sir, can we also say if there are no identical elements in the same ordered pair, they'll be optically active?
No identical.
Like if all the elements in the ordered pair are different, like there's no AA, AB or something, like AA, BB and all, if there's AB, BC, AC and all, then it'll be optically active. Is it right to say that?
Optically active, we just check the plane of symmetry. Okay, we'll
Okay,
discuss
sir.
that. Optically active, optical isomerism we'll discuss after this. Geometrical isomerism, we'll see that. So we'll check the plane of symmetry over there, nothing much.
Oh, okay, sir.
Okay. Yeah, M, A, B, C, D, E, F type all are optically active. There is no plane of symmetry there. You can say that. Okay. One important example here, the last one, is this. We have MA3B3 type, and this one they have asked many times in the exam, JEE. For example, we have CO, NO2 3, NH3, this one. Okay. So whenever you get this kind of question, you represent it this way. Then it will be easier for you to analyze. Okay, molecule is this, and this is the representation we have. So we can represent two structure for this, and in this case we do not, write cis or trans term here. So we have metal here. One possibility where all the A present at 90 degree, right? All the A present at, we can place like it this way. One on the top, on the bottom we'll have B, 1 and then 2 and then 3. 2 and then 3 like this. This is one way. Another way is what? We'll have metal here. A will place over here. B here. A again here. So this molecule you see, okay, so this looks like the face of a triangle here. See this? This also looks like the face of a triangle. Right? This particular representation, we call it as facial isomer. This one is facial isomer, and we call it as FAC. In this one, the position of ligands are on the meridian of an octahedron. This position and this position, meridian of an octahedron, and this we call it as meridonal isomer. Just this term you have to memorize, nothing much. FAC and MER in short. So always remember Ma3B3 type, we represent it this way, and we do not, write down cis or trans isomer here, but we write down facial, that is FAC or MER isomer.
So, observe that here NO2 is an ambidentate ligand.
No, NO2 is, whether you write here or not, NO2 has the tendency of to behave as an ambidentate ligand, but here nitrogen is the donor atom.
Okay.
If it is oxygen, then it would be written over there ONO, not NO2.
Okay.
Sir, how do we write cis or trans for the others before this?
For which one?
For any of the others, like
Trans.
A3, B2C or something.
I'll tell you. I'll go to the beginning.
So one second.
What?
So I just copy this.
Cis and trans, we just see the identical ligand and their position. I'll explain you one or two examples.
Okay, sir.
Thank you, sir.
See, the simplest one is MA4B2 type. Okay, so in that case, you consider the position of B over there. In one of the isomer, the 2B ligand present at 90 degree, and in another one, the 2B ligand present at 180 degree.
Yes, sir.
This one.
Yes, sir. That one you explained, sir. Sir, after that, the next one also you explained. After that, like MA3B, CD or something.
And I got the point. Suppose you're talking about this one, right? Here, cis and trans, okay?
So this also you told, sir, you can take any one and then write with respect.
And which one you're talking about?
Next one, sir, like supposing there are 4 ligands, MA3,
This one?
BCD. No, sir, MA3, BCD or MA2, B2, C2.
So in that case, usually we do not write anyone you can take at that. See, suppose we have MA3, according to you, MA3BCD type, correct?
Yes.
Okay. So what we can write, you draw the structure. We can write A here, A, then B, C, D, we can write like this, okay? Why with respect to A you cannot define? Because the 2A here present at 180 as well as 90, correct? So if you
Yes.
change the position here, like for example, we have metal here, and what change we can do? We can do one thing. We can have this A place here and D on the top, B and C. Correct. So here you see all A are at 90 degree. Correct. But if you look at the two structure here, you can take B and D. With respect to B and D, you can differentiate the two. It is trans here and it is cis here. Any two ligands you can take if the structure is given. But we cannot define, it's very, it depends upon the structure what is given. With respect to A, you cannot define because A are at 180 as well as 90 degree also. So this we cannot take. Any two ligands out of the 3 BCD we can take for this. Like in this one, this is one possible isomer. This is another possible isomer. Do we have another possibility in this?
Yes,
We can have another possibility also, right?
Yes, sir.
B and C are at 180 degree. Many structures you can draw. B and C here. D let it be as it is. A and A.
Okay. Okay, sir. Understood.
So this also you can take. So basically, there is no proper definition of cis and trans. They just said that based on the angle we can say. But then depending upon the structure, you have to choose. Okay, with respect to this it is cis or this it is trans. Right?
Okay, sir. Got it.
Fine. So this is we have done for all the possibility we have done. for octahedral complex with only monodentate ligand. It is also possible that in the complex we'll have one bidentate ligand and other are monodentate ligand, or more than one bidentate ligand. That is also possible. Write down the next type here.
So can you go to the previous page?
What?
The board 6, sir.
Board number 6, you said? This one?
Yes, sir. Yes, sir. Thank you, sir.
Okay, so in all these molecules, the one which is the most important one and which they have asked question many is this one, MA3B3 type, that is facial and meridonal. How do we write down facial and meridonal? Facial is all the A identical ligand present at 90 degree. You see the position of this, this and this. All these are at 90 degree. When one of this you place at 180, you exchange the position of this two. You get meridonal, which is this one, right? So here you see the 2A, one of the A present at 90 degree from the other A ligand and 180 degree from the other A ligand. This is present at 90 as well as 180, and same thing we have for B also. 180 with respect to this, 90 with respect to this. So basically, if you interchange the position here, you'll get meridonal. Why we call it as meridonal? That is not required, but it says like it is present, the ligands are present at the meridonal of the octahedron, hence it is meridonal, nothing much. Okay? But you should know how to write down the facial or meridional isomer. That is what I explained. All at 90 degree, 2 at 90, 1 at 180. Okay, now the next one is compounds containing, second type, write down. Compounds containing bidentate ligand. So for example, the first one we have MAAA4 type. What do you understand by this complex?
So 1 is bidentate, 4 is monodentate, so 6.
One is identical bidentate ligand, and other one and 4 ligands are monodentate, right? Identical monodentate ligand. Coordination number is 6 for this complex. When coordination number is 6, the geometry is octahedral, and to draw the structure, we'll draw a square. What you have to keep in mind here, whenever you have bidentate ligand, okay, whether it is symmetrical or unsymmetrical, the two donor atom, in this case we have A and A, two donor atom must present at 90 degree. 180 you cannot place. Must present at 90 degree, right? For example, you see ethylene diamine. Ethylene diamine, I'm just trying to make you understand this. We have nitrogen is a donor atom, and this nitrogen is connected with carbon, CH2, CH2, another nitrogen atom like this, and it donates electron and forms a complex like this. So these two donor atoms are connected by this bond, right? This bond or this connection we represent by like this. This means AA atoms are joined together, the bonds of the ligand that we have here. So maybe if you present this A at 180, the bond length is not enough, or if it is enough also, then there will be more strain, and hence we do not place this two atom at 180 degree to each other. Always keep that in mind. For bidentate ligand, the position occupied by the donor atoms of bidentate ligand is always at 90 degree. So this is the the position of the two bidentate ligands, and all A present like this. Understood? How many GIs are possible in this complex?
Only one.
One only,
One.
like only one structure, no GI.
Only one structure, so no GI. Okay. GI we always write in a pair. So one structure cannot give you pair, right? So no GI possible. Because all these positions are equivalent. It does not matter whether you place this A over here, or this A over here, or this A over here. Right? So there's no GI for this one. If you look at the second example, we have MAA and A3B type. Tell me how many GI. One more thing we can write here, like similarly, just to save the time in the exam, you can write AA, then we can write again AA. Only one possibility. How many GI is possible in this? Understood, Aditya? Aditya Manjunath. Geometrical isomer possible with the relative position, no? You change the position of A and check whether you are getting different structure or not. So the possible structure here is AA, then we'll write AA, and then we'll write AB. See, this is not the method. It is not given in the book. But to understand or to save time to count the number of GI, it is always better than to draw the structure in the exam. Okay. Another one is what? AA we write as it is. With A we'll write down B, and then AA, and we do not have any other possibilities. So 2 GI possible for this one.
So, in the previous one, you'll get AA, capital A, small a, two pairs of that. And then capital A, small a.
No, you won't. Capital A, you won't get.
Oh, right. That is the rule, right? It should bidentate should always be at 90.
Right, 90 degrees. So emotional हो कि इसको यहाँ नहीं place करना है.
Okay, sure, sir.
Okay. So it is always at 90 degrees. So you won't have the pair of AA. ठीक है, ये pair नहीं बन सकता है, never. Okay. Next one you see, third type, MAA, A2B2. Tell me the number of GI. MAA, ABCD. MAA 3. Okay, so here it would be AA we have, then we have AA and BB. AB, 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 A. Okay, in this one we'll write, sorry, AA, then AB, and then CD, and AC, then AB, AD, and then we have AD, AB, then CD, right? Similarly, we can draw 3 more isomer here.
So the first and third are the same.
First and third, is it? Acha, CD I have written here, AD. क्या कर दिया मैंने? AD, it should be AC here. AC. Is it fine?
Yes.
Okay.
Sir, I think you can have one more in the fourth one. Yeah.
We have 6 GI possible.
Sir,
Which
ACAD. So
What?
ACAD.
AC,
AD.
AD, and
AB.
AB. 6 GI possible like this. Okay. And again, I'm telling you, this thing you do not write in your school exam or in board exam. Okay. This obviously gives you an idea that how many GI possible, and you won't get wrong answer over here if you could find the number of GI like this. Okay.
So this portion is deleted.
Sorry,
So this portion is deleted.
your voice is not coming, Anjali, properly.
So she said that this portion is deleted for our school.
Actually, it's not there. Fine. Then it's fine. They won't ask you this. But like every year, I used to, say this in the exam. This is just for the information how to count the number of GIs without drawing the structure. Okay. Yeah, that's fine. AA3 type is, I'll draw the structure for this one. Okay, then only you will understand that how the structure possible for this one. You see, we have a square bipyramidal. Metal is here. Then A, right? All our bidentate ligands must present at 90 degree. So we can say these two are connected. These two are connected, and these two are connected. One possibility is this. Okay. Another one is what? Metal present here. A, this two, oh sorry. We can write next what? Tell me, do you have any GI possible? Can we draw any structure here? If I take this to here, for example, right, then if you take this one, we'll have the same structure. If you take this one, this one, then it is not possible because these two are at 180 degree. Are you getting me?
So whatever said and done, one pair will always be at 180 degrees.
Yes, that's why in this we do not have GI. No GI possible in this one, right? But why I have done this, if you look at this molecule, so this is not possible. So let me just remove it. It is not possible. But if you look at this molecule here, if I take unsymmetrical ligand, which is nothing but this, MAB3 type. In this, is it possible?
In the previous one, case 5, we'll have to write A, capital A, no? Even if you want to get one structure, we have to write capital A. So that means one pair of A's are at 180 degree with each other.
This you're talking about?
Yes, sir. If we follow that coordinate system, ordered pair.
What I said is that the two atoms, donor atoms, right, which belongs to the same molecule, same ligand, should not be there at 180 degree.
Okay, sir.
Means you have multiple bidentate. No, EN has, suppose ethylene diamine. So one ethylene diamine placed here, another one placed here. What is so big deal into this?
Okay, sir. But then if you write the ordered pair, the A and all, you have to write A. You have no choice, no?
What I said, this is also not a genuine method. We don't write like this. This is just I have given you to count the number of GIs. Okay.
Okay, sir.
Here there is no sense of writing it down. A does not make any sense. So not
yes, sir.
required. And however, in this is not possible. So that's how it is. Okay. In this
yes,
one, how
got it,
many
sir.
is possible? The last one?
So there's no GI here also.
No GI.
Don't think so.
No, sir.
Why no? Two. I don't know. I'm not getting your voice properly today for all of you. I think some network problem. Anyways, then we have, suppose I place A here and B here. Right. Then I can place A here and B here. And next is A here and B here. Right. So we can say these two are connected. These are connected and these are connected. Another possibility, I think one more should be there. Mm. One, two. Then we can write A here and A here, B here and B here. This one possible?
Sounds the same.
Is it? It's not same.
Oh yeah. Yes, sir.
See, these two GI is possible for this one.
So how are they different? So could you explain?
Yeah, I'll explain. No, it's not possible. GI mirror image is not possible here. I'll tell you in this one, because we are talking about geometrical isomerism. So mirror image we are not considering. See here, it's very simple and clear. You can understand this. Look at the relative position of all A here. We have these two at 90, this two at 90, but this is at 180, right? In this one, you see all A placed at 90 degree. 90,
Oh yes, sir. Yes.
90 and 90. These two are different. Relative position is different here. Two molecules are different. But in the previous one, it was A only everywhere, right? A. So if you draw this one also, the relative position is same. So no GI in the previous case. Right? It looks like similar, but the relative position of A is different in the two molecules.
Yes, sir. What?
So in fact, this one is what we can say A, and A here. Yeah, that's fine. Let it. So these are two structure we have. The second one here, if you compare this with the facial and meridional one, this one all A present at 90. So this one is FAC and this one is MER. It looks like different, but all A are at 90 here also, and in facial also all A was at 90. Got it? Yeah, so this is it for coordination number 6. Here the coordination number 6 is the most important one. Okay, most important one. They ask mainly from coordination number 6 only. Optical isomerism will discuss finishing geometrical. Okay, so next you write down for
1
coordination.
minute, sir.
Sorry.
Sir, 1 minute. I was copying that, sir. Just a second, sir. Done, sir. Thank you.
So next is write down coordination number 4. Coordination number 4. If you have complex contains all monodentate ligand. All monodentate ligand. For example, the first one is MA4 type. Do we have any GI in this? No GI present. Yes. If you write down MA3B type, what is the number of GI? MA2B2, MA2BC, MABCD. Number of GIs in this. Done. So in this one, we have no GI. In this one, we have cis and trans 2 GI possible. If we want to write down, just AA and BB. In this one, we have AA, BC. So we have only 2 GI. That is A, B, C. And we have AB, AC type in this. And here we have 1. We can write AB, CD together. Or we can write AC, BD together. Or we can write AD, BC. Any other possibility? We have only 3 GI possible. AB will be also possible. I've written here too. Okay, so since we have coordination number 4, so we'll get 2 pair here, right? Third pair won't be there. If we have bidentate ligand in this, then what are the possibilities for bidentate ligand? We have MAA, A2 type, MAA, AB type, MAB, A2 type, MAA, 2 type, MAA, B type, MAA, D type, MAB, D type, MAB, AB type. Try all this.
Sir, how do we know if it's square, plane, or tetrahedron?
Done?
1 minute, sir.
And what about the last one? Square planar or tetrahedral triple we can understand only if you know the geometry, sorry, hybridization. If you are getting it as sp3, it is tetrahedral, otherwise sp2 gives square planar. So hybridization gives you this information actually.
Yes. So we'll need to know that to know the isomers or not?
No, in the complex, when you use that VBT, no, with that, whatever hybridization you are getting, you will get that. Because in this case, that is there in case of trigonal bipyramid, where we have to, where we have, you can talk about this thing. What is the dipole moment? You can talk about whether dipole moment is 0 or not. Or you can talk about number of bond lengths are same or different, which gives you square pyramidal geometry also, right? But in case of coordination number 4, you will get whatever the geometry, whatever the hybridization we have, according to that, you will get the geometry.
Yes, sir, yes.
If it is square planar, you will get DSP2 hybridization.
Yes, sir, yes, sir, I understood that.
Okay. Now, in this one, you see all these molecules from number 1 to number 6. The number of GIs are 0. No GI possible in all these molecules. You can think of by drawing the structure, you'll get no geometrical isomerism. From 1 to 6. Okay. One thing you can keep in mind, if coordination number is 4 and the ligand is symmetrical bidentate, coordination number 4, ligand is symmetrical bidentate, then GI is not possible. That you can keep in mind. Right? Coordination number 4, symmetrical bidentate, no GI possible. Here we have 2 GI, and here we have again 2 GI possible. The possibility is AA, BB, and we can also write AB, BA. Here also similar way we can write down. We have AC, BD, and we have AD, BC. Understood? So these are the few examples we have done for coordination number 4 and 6. Okay. Now we'll see the optical isomerism. We don't have much in this, only few examples we need to discuss in optical isomerism. Write down the heading optical isomerism. So you know the logic behind optical isomerism. It is the property of a molecule towards plane polarized light. So I'm not going to give you the basic understanding what is optical isomerism and all that we already know. Okay, what you need to know here, first of all linear geometry, whatever linear geometry we have, they do not show optical isomerism. So write down the first point. Linear geometry does not show optical activity or optical isomerism. Because suppose we have square planar, right? So in the square planar geometry, the plane in which the molecule is present, along that plane only we have a plane of symmetry, right? We can divide the molecule into two equal halves along that plane, and hence we have a plane of symmetry. So there is no optical isomerism possible for square planar geometry or any planar geometry, like linear, trigonal planar, right? Square planar. Optical isomerism is not possible. Okay. Next, write down tetrahedral geometry. Tetrahedral geometry shows optical isomerism. Tetrahedral geometry shows optical isomerism if and only if all the four ligands are different. All the four ligands are different. Then only we do not have any plane of symmetry there.
So could you just repeat that?
Yeah. Tetrahedral geometry shows optical isomerism. Tetrahedral geometry shows optical isomerism if all the four ligands are different. If any two are same, optical isomerism is not possible. Because when four ligands are different, then only we do not have any plane of symmetry. Okay?
Yes, sir. Thank you, sir.
Okay, next write down.
So what if it's a bidentate ligand?
Wait, I'll do. Wait. Write down next. The molecule or the complex which shows optical isomerism. The complexes which shows optical isomerism must contains or not must contain, which shows optical isomerism, may contain at least one symmetrical bidentate ligand. At least one symmetrical bidentate ligand. Next one.
So could you just repeat? Sorry.
If the complex contains unsymmetrical bidentate ligand, then also optical isomerism possible, may possible. Means if all these things are there, then you can think of optical isomerism. Unsymmetrical bidentate ligand, then optical isomerism possible. Last point. Trans isomers trans isomers contains plane of symmetry. Trans isomer contains plane of symmetry, hence does not show optical isomerism. Hence does not show optical isomerism. Okay, there are a few complexes which shows optical isomerism. I'll write down the general formula here of the complex. This type of complex, it shows optical isomerism. Ma2 B2 C2 type, we have discussed this. One of the combination shows optical activity. MAB CDEF type, optically active. If you have MAA, this is also optically active. MAA2 type A2, this is also optically active. AA2 type AB, this is also optically active. MAB3 type, this is also optically active. 1 minute, I'm coming. Copy this. Done?
Yes, sir.
Okay. Now, this two we have already seen. This complex, you see the structure of this MAA3 type. How do we draw the structure here? So, only one possibility we have, one structure we can draw, where all the A atoms present like this. Tell me, do you have any symmetry here? All A atoms are there. Along the plane of the square, do you have symmetry?
Sir, could you please repeat?
Yeah, tell me.
No, sir. Can you please repeat that, sir? I didn't hear you.
Along the plane of the square, do we have symmetry?
No, sir, I don't think so.
No, sir.
No. Okay. Some of you are saying yes, some of you are saying no. We do not have. Why we do not have? If you take a plane here, along the plane of the square, this, we do not have mirror image over here. It looks like, right?
So the position of the bidentate.
What? See, fine. In this molecule, obviously I have given over there that this molecule shows optical isomerism. So we do not have plane of symmetry here, no POS in this. Right. There is plane of symmetry. Optical activity is not possible. Yes. So actually what happens here, this, you may get mirror image of this A over here. Suppose it is coming out of the plane and it is below the plane we have. So this bond, this A bond is coming above this diagonal, right? This MA bond, it is just above it. And this bond is below this diagonal, yes or no? Can you imagine this?
Yes, sir.
Yes, tell me. Right? That's why this thing, plane of symmetry is not possible in this one. Okay? The same logic you can apply to these, complex also. MAA2, A2 time. The only difference is what? This AA2 is fine. We can have two monodentate Hello.
Yes, sir.
Lost the connection. Just a second. Yes. Can you hear me?
Yes, sir.
Okay. So this is the plane of symmetry we have. All the examples, if you write down A2 type here, or if you write down MAA2, AB type here, all these are optically active because of this one. There's one example here, which is that facial and meridional MA3B3 type. MA3B3, this you have to memorize, okay? Because one of the molecule you can easily understand there is plane of symmetry. But other one, it is not visible in the complex, right? Because it has alternative axis of symmetry, which is actually you need to change the position, angle, and then you have to imagine it, right? So that's a very difficult thing to visualize in the complex. So you have to memorize this one. First of all, I'll draw the structure. The two possible structure here is one is facial, other one is meridional. So 2 square, metal at the center, and facial is all A are at 90 degrees. 1, 2, 3, all A are at 90 degrees. Meridional is, I'll draw it, right? B, B, and B. This is facial. All A are at 90 degree. Meridional is 1A here. Basically, these two positions you have to interchange. You'll get meridional. So we have A, here we get B, here we have A, B, and B. This is meridional. In this one, it is very, along this plane, we'll have the plane of symmetry, this A and this A. We'll have the mirror image. So along this plane, we have the plane of symmetry, right? So in this, we can say we have POS, and hence no optical isomerism this molecule shows, okay? In this molecule, it's difficult to visualize, but this molecule contains contains alternative axis of symmetry, right? So you just keep this in mind. Sometimes they ask this question because we cannot see here, like if you try to imagine, you won't get here any kind of plane of symmetry, because this thing you cannot imagine. It's very difficult to visualize. No, you have to draw the structure 2-3 times, and then you have to see the plane of symmetry. This is something is very difficult to visualize. So what I'm telling you here, MA3B3 type, first of all, the molecule is optically inactive. There's no second thought about it. Optically inactive, right? If they ask you this question also, then also you keep this in mind. This molecule, however, plane of symmetry we cannot visualize in this, but this molecule, it contains alternative axis of symmetry, right? Any kind of symmetry is there, which makes the molecule optically inactive, no optical isomerism. Okay. Apart from this, I have given you what all different formulas we have, general formulas which shows optical activity. You need to just check the plane of symmetry by drawing the structure if you do not memorize. That's the method we have. Otherwise, you can keep this one as well.
Excuse me, sir. What did you say? AOS is alternating axis of. Could you just explain that, sir? What it means?
We can do that. But usually what happens, you have to keep this in mind, because in any molecule, you cannot, identify this particular axis of symmetry. That's why mostly we don't talk about it. It is an element of symmetry that we generally discuss in this thing, solid state. Okay, center of symmetry, plane of symmetry, alternative axis of symmetry. This rarely exists, but it is there. So we have. So what happens? You have to change the position into this, and then you can find out the alternative axis of symmetry. Okay, just a second. Do one thing. You let it be here. We'll discuss solid state. In that only, I'll tell you how to do this, because you need to draw the structure and then change the position. You'll get one particular structure here. Again, you change the position, another structure you get, and then you can compare the first and third like that. You can say there is an alternative exosymmetry present. Okay, so let it be. We'll discuss a little bit this in solid state. Okay, we'll do that. Not much important, but here you need to understand that B3 type. Okay, it contains, first of all, it does not show optical activity, right? And one of the molecules, the left side I have drawn. Okay, in that molecule we have alternative axis of symmetry present, right? And that's why it is optically inactive, which actually you could not see because it does not look like any kind of symmetry present into this molecule. You want to take just a second. What?
Sir, where exactly is the POS for the B case?
POS for the
B case.
this one.
Yes, sir.
Along the plane of the square.
Oh, the mirror image of A is A itself.
Right. It's not bidentate. No, it's not connected to the corner plane.
Oh, okay, sir.
Right. If it is connected, then it would be difficult. Right, but here it is there because it's not bidentate again. Okay.
Yes, sir. Understood, sir.
One second. I'll show you one figure here. You'll understand the alternative axis of symmetry. Another page. Hold on, guys. Here. See, this way we generally understand optically alternative axis of symmetry. Any molecule, if it is given like this, okay. If you rotate this by 90 degree, right, like this 2 comes over here, this 3 comes over here, 4 comes over, we'll get this. Okay. One second, I'm getting it. Okay, if you rotate this by 90 degree, or if you keep on rotating, okay, you will get a state where the first molecule, this is structure, and the other one completely overlaps. Okay, it's look like identical to each other. And that particular thing, we call it as alternative axis of symmetry. Here also the complete structure is not drawn. Okay, four-fold axis of symmetry we have here. Means you need to draw it, rotate it 4 times like this. Okay, so this kind of symmetry, that's what I was telling you. Even if you understand this, you cannot imagine in this in the molecule. Right? It's very difficult to imagine. That's why MA3B3. Why I have given you this example, because they have asked this question in the exam. Alternative axis of symmetry we cannot visualize in the molecule. So when you look at the structure here, it looks like there is no symmetry present here, right? Because it has alternative axis of symmetry. That's why I said you have to memorize this here. You need to rotate the molecule, and then if you find one state where the 2 molecules looks like completely identical, then we consider alternative axis of symmetry. This comes under elements of symmetry, where we have center of symmetry, plane of symmetry, 2-fold axis of symmetry, 4-fold, 6-fold axis of symmetry. There are many things comes into this. Okay. Even in solid state also, we won't discuss this in detail. Mainly we'll see center of symmetry and plane of symmetry, because that is only thing we need to take care of. So this is it for this chapter. Okay, coordination compound, we have done this thing in detail. Isomerism part, especially coordination number 6, optical isomerism, is the most important one. They ask questions on hybridization related also, BBT, CFT also they ask questions based on that. So there are many different kinds of questions that forms here. We have seen that on the basis of isomerism, they have asked question many times, and BBT they have asked many times. One last thing I will tell you, you will also see some color-based question in this chapter. Okay, what is color this complex shows? So color of the complex is because of the DD transition between D and D orbital. And if D subshell contains any unpaired electron, then only it shows color. If there is no electron in the D subshell, it does not show any color, right? So DD transition, the orbital gap that we have, the energy gap that we have, this energy, it corresponds to one particular wavelength, and corresponds to that only we have the color of the complex. So obviously this color of the complex we cannot find out logically. We have the way to find out the color, because suppose if you solve this and you get the lambda, right, lambda value you got, then how do you memorize that? Wavelength of each color you cannot memorize, right? So you can find out the mathematical value of it, but still you cannot say that this wavelength corresponds to which color. It is impossible to memorize the wavelength of each color. That's why the color related complex that you get, what you do, metals with in a given particular oxidation state, it shows a definite, it shows a color. You make a note of it. Okay, you will hardly have 8 to 10 different types of ions with metals. So make a note of it and try to keep this in mind before the exam. You can give it a revision of all these, right? These kind of things you'll revise in last week of the exam actually. So that you can do. Fine guys, so we are done with this coordination compound. Okay, we are going to start with a new chapter, and that is physical chemistry. Solution we are going to start with. Okay,